Document databases for unstructured data, for dynamic information, you know, JSON-like, things like that. Key value stores for quick access. Simple query by key. That's it. You don't know the content of your data. Column stores for quick elaboration on column data, so single structured data. Graph databases to manage relationships. Now, I divided this in two categories. Graph databases are alone on the right. Why? Just because graph databases are the only NoSQL solution that can manage relationships. In key value stores, you cannot manage relationships. The same is in document databases. Column stores are not designed to do that, of course. Graph databases are. So why? Most NoSQLs just avoid to manage relationships. Well, the answer is easy, because it's tricky. It's hard to manage relationships at scale, efficiently, and it's hard to manage them in general. Do you remember this? This is from the old relational world. Two tables, customer and address, a big join table in the middle. What's that in your domain? That's nothing. That's an artificial table put there only to manage relationships. And the relationship is something, let's say, formal, but not physical. I mean, it's not a concept in the database. It's just a convention. When you want to calculate the relationship, when you want to know the customer address, you have to do a join. You have to do calculation. And if you want the same address again and again and again, you have to do the join again and again. And it's calculation every time. So this is how old relational databases, the relational model, tried to solve this. What's wrong with this? The wrong part is that it involves calculation every time. And if you have to do multiple joins, so if you're not interested in just customer and address, but if you want a friend of friend of friend of friend in a social network, you have to do multiple joins. And you pass from small tables, let's say a few millions of records, to billions or thousands of billions of possible combinations for the result set. And the relational database cannot manage that. The performance of the join operation is logarithmic because it typically relies on a tree-based index. So the cost of the single join, the single, let's say, traversal for a single foreign key, let's say, depends on the size of the database. So small data set, quick joins. Big data set, slow joins. So the database size grows up, the performance goes down. That's the problem. What's the solution? Well, the only solution that we have now is graph databases. So NoSQL solved this with graph databases. What's a graph database? It's a representation as a database of the graph model. A quick crash course of graph theory. Couple of slides. A graph is just a set of vertices and edges. Vertices can be called nodes, edges can be called links, but anyway, all you know what I'm talking about. By the way, how many of you are developers? Please raise your hands. Oh, a lot of people. So happy. What's a graph? A graph is a set of both vertices and edges. You can connect a vertex to another vertex with an edge. Every vertex has a label or type, and the same is for an edge. Every vertex and every edge can have attributes, multiple attributes. In the property graph model, properties are simple types, numbers or strings, that's it. And most graph databases do that, just represent numbers and strings as vertex and edge attributes. Cardinality is not a problem. You don't need join tables in the middle. Edges are first-class citizens. You can add as many edges as you want between two vertices. One-to-one, single edge. Many-to-many, multiple edges. You don't change the model. You don't have to add artificial information in the middle. There's no way and there's no need to add artificial information. That's a natural model. There are no tables. There are points in your space, vertices, and connections, relationships, edges. That's extremely natural. And then there are attributes, of course. Congratulations, this is your diploma in graph theory, at least. The graph theory you need to start using a graph database. That's it. But I mean, the question remains, how does a graph database manage relationships? Why is it more efficient than a relational database? I say a true graph database because a relational database with a graph layer on top is not a real graph database, and also, it's true also for other data models. In a graph database, every element that is a vertex or is an edge has an immutable identity that is a physical pointer. In OrientDB, we have a record ID that is made of cluster ID and cluster position. The cluster ID, the first number is the file where that vertex is. The second number is the physical position where that vertex is in that file. So if you are looking for a vertex number 1355, you can open the file number 13 and look at position 55. It's there. No calculation. It's just there. The same is for edges. Now, once you have these elements, you can connect them together. You have properties. So you can have a property on the vertex called out that contains a record ID, the value of the position of the edge. So traversing from the vertex to the edge just means reading a property and doing a physical lookup to a physical position that is 2211. File 22, position 11. It's there. O1, constant time traversal. This is a pure graph engine. Now, how does it scale when your database grows up? I mean, if you have 1 record or 10 records, you have to traverse that. You just keep the record you want. You read the record ID of your edge, and you look into that file at that position. That's fine. But what does it happen if you have billions of records? Just nothing. No indexes involved, nothing. You just open the file, and you look at that position. That's it. It scales with the size. The traversal cost is constant. It does not depend on the size of your database. Of course, you have these pointers on all the paths. So you have on the first vertex, you have the pointer to the edge. In the edge, you have pointers to both vertices. And on the other side, you have the reverse pointer to the edge. So you can traverse the relationship at constant time, but you can also traverse the relationship backwards with the same cost. This means that what was impossible with relational database, like doing 100 or 1,000 join operations in the same query, now is trivial. In a graph database, doing a full scan of a cluster, so reading records one by one, or doing a deep traversal, friend of friend of friend of friend, is the same. The cost, apart from cache hits and so on, I mean technical stuff at a low level, the cost to the record access is exactly the same. So you can stop thinking about, oh, I have 5 joins in my query, this will never work. It will work. So the real difference is that graph databases create relationships when you create based on how they manage data complexity and how they manage relationship efficiently. You have document stores. They can manage complex data structures, nested documents, but they cannot manage relationships. You have graph databases that cannot manage complex records. Typically, they do not have multi-statement transactions and so on as well, but they can manage relationships very well. Here you have key value stores. They're very good at accessing data quickly. They're extremely efficient, but they don't support any data complexity or any relationship management. So there's no perfect solution. I mean, in the top right quadrant, there's nothing. So what happens is this. You have a relational database that manages operational stuff, I mean, transactions. You have a document database that stores unstructured data, JSON documents, things that come from unstructured data sources. You have a graph database that is needed to do traversal efficiently. Maybe you have a cache, a key value store for quick access to data, fresh data, and so on. And your application is in the middle and has to talk to all of them. You need ETL. You have to keep all these data sources aligned. So we solved one problem at a time. I mean, document database solved one problem. Graph database solved another problem. Semi-structured data, relationships, quick access by key, and so on. But we created a bunch of new problems. This is the result of first generation NoSQL. That is, no standard. Every single product has a different query language. Multiple vendors. How many licenses do you need in this system? ETL, synchronization, data consistency between data sources. What about performance and what about reliability? I mean, how many moving parts do you have here? A lot of them. So, from the experience of all this, database vendors, NoSQL database vendors, and OrientDB as well. I mean, OrientDB started with that actually. But anyway, the NoSQL world is evolving to a second generation that is a multi-model generation. That means that having a single data store that only implements a single data model is not enough in general, because your application needs multiple data models. So what's a multimodal database? That's a database that includes multiple first generation NoSQL models. So document, graph, key value, object. 10 years ago, 15 years ago, there was a trend that was object databases. Now nobody talks about object databases, but they were there. Having a multimodal database would mean having only one product to learn and to maintain. No multiple moving parts. Only a vendor, a single license, a single contract, a single person to blame if something is wrong. No ETL, no synchronization. That means completely removing that part of the problem, and the whole stuff is easier to develop, to test, to predict how it will work. So let's see how OrientDB does all this. OrientDB is a multimodal database. It is a document store, native document store. It's a native graph database. That means that it implements physical links that is called index-free adjacency. So adjacency that does not need indexes for performance. But many are things. Now, every element in OrientDB is a document, like a JSON document. This slide contains a lot of information. I will tell you it piece by piece. But let's read it line by line. What you see here on the left is a representation of a simple document. The document has a record ID, 12382. That's the physical position of the record in the database. The record has a class. A class is like a table in a relational database, or like a collection in MongoDB, for example, with a slight difference that this is called a class. And it's not just to say, it's a class. I mean, you can define class hierarchies in OrientDB. A class can have superclasses, subclasses with multiple inheritance. You can do polymorphic queries. You can have class customer that is a subclass of person, or that is a subclass of entity, and so on. And you can have subclasses of customer that, I don't know, premium customer. And you can do select star from customer and have both customers and premium customers. So the same concept you use in your object-oriented programming language exists in the object-oriented query language and data store. Then we have properties. String properties, number properties, complex properties. You see, the details is an inner JSON. It's a complex object. It could be nested. Again, you could have nested elements inside nested elements. You can have list attributes, so collection attributes. You can also have link attributes, so attributes that point to other record IDs. That's how graph is implemented, nothing more. So every document can be represented as a JSON. This is the same as what you can find in document databases, classical document databases, with another little difference. Document databases do not enforce a schema. A document database just says, put whatever you want in your database. I won't check anything. Put numbers, strings, new attributes, and so on. In OrientDB, by default, you can do that. You just define the class customer, and then you put inside it name, surname, and so on. But if you want, you can enforce a schema. That can be a partial schema. Let's say name and surname are strings. They must be at least 3 characters long and at most 20 characters long. Age is a number, an integer number, and so on. And then you can add new attributes if you want. Or it can be a strict schema. I mean, you can say the class is made of 3 attributes. You cannot have 4. 3 attributes, name, surname, and age. That's it. All this can be indexed, of course. You can define indexes on schema properties, and so on. This is extremely developer-friendly. I mean, you can start developing, you can start just pushing data inside your database without defining any schema. But at a certain point, you will see that you need some validation, that your application cannot tolerate that someone does the wrong query and stores an attribute with the wrong name or with the wrong value. So you just define a schema at that point, and the database will start validating your data. So here's where multimodal database is. A multimodal database is mainly a database that has both the advantages of a document store and a graph store, plus concept from object orientation, plus concept from key value stores. We have manual indexes that you can use like key value stores, plus other things that we will see. OrientDB is a true graph database, a true document database. That means that it's both a native graph engine and a native document engine. I'm going a little fast. I'd like to show you something practically. OrientDB supports Tinkerpop, that is a standard for graph databases, Tinkerpop API. The main query language is SQL. What? I mean, it's a NoSQL product. Yeah, but how many of you know SQL? Raise your hands, please. So you know how to query OrientDB. This is why we decided to adopt SQL with extensions, of course, as our main programming query language. It supports JDBC. If you want, you can connect OrientDB to your business intelligence tools. It has a native HTTP REST JSON interface. You can query it with that, but it also has a binary protocol that is faster, of course, than the HTTP interface, and that on top of that, we have native drivers for Java, Node.js, Scala, Python, PHP. And we also have community-contributed drivers for .NET, C++, and many, many more. The core of OrientDB is quite small. If you download OrientDB, it's, in total, it's 30 megabytes. A few jar files. The core, the package includes Tinkerpop, additional APIs. Some of them, I mean, you won't need all of them. OrientDB also has a strong focus on enterprise-related topics like security. It supports encryption at rest, basic HTTP authentication and Kerberos authentication, record level security. OrientDB is a complex user role system. So you can have users with different permissions of read-write permissions. And you can also define ownership of single records, 2 single groups or single users. So that if 2 users do the same query, they see different results just because one of the two is not allowed to see that record. This is very powerful in many situations. And in the Enterprise Edition, there's also auditing facilities. It supports encryption, SSL and so on, Kerberos, encryption, REST, if you want extreme security, if you don't want anyone to see your data, even if they access your file system. Full backup restore, delta backup, and so on, a lot of stuff. There's also a couple of nice tools like Teleporter that was just released that is a connector to relational databases. You just can plug OrientDB to a relational database. Teleporter will just infer the graph schema from your relational schema and will import all your data inside OrientDB so that you can start playing immediately. OrientDB is also designed to scale as a multi-master architecture with tunable consistency. That means that that you can have you have a quorum-based consistency, so you can have asynchronous eventual consistency or synchronous full consistency between replicas and so on. It's almost zero configuration. You can start 2 nodes in distributed mode, and the first node will just start alone and will start working. Then you start the second one. It will discover the other node, will just join the cluster, and you will have 2 nodes replicating without any configuration. By default, it works with multicast. So if your network supports it, it's already there. You just have to run a script and it works. Another nice thing about OrientDB is that it's written in Java, full Java. It can run as a single standalone node. So you start it as if you started Oracle and you connect via HTTP, but you can also embed OrientDB inside your application so that the database runs inside the same virtual machine of your Java process. That means no network communication, no marshalling and marshalling of records, of result sets, and so on. You access directly the storage, and it's 10 times faster than communicating over the network. I mean, that's just network communication. It has a cost. It can also work with a multi-master replica, so you can have multiple nodes of OrientDB that work in replica, and your application can communicate with all the nodes with fault tolerance, high availability, and all the rest, load balancing. We just released version 2.2 yesterday, actually, that has native load balancing at the client side. And you can also have a mixed approach. So some nodes run embedded, some nodes run standalone, and the embedded nodes are automatically in sync with other replicas. That's extremely powerful. I mean, you can choose how you want to deploy your architecture. Here there's a list of features just to be complete. OrientDB supports ACID transactions, SQL of course, custom data types. You can embed documents. There's a basic support for sharding, but it will be improved in next releases. It supports server-side functions, but I will show you something practically. And maybe the most important thing is that it's free open source software. You can download it. You can download the source code from GitHub. You can contribute. Contribute, please. That's easy. There are some of our issues or some of our feature requests on GitHub are flagged as contributor friendly. You can take a look at that and see that it's not impossible. It's just plain Java. Apache 2 license means that you can use it in your projects without paying €1 single to OrientDB. You can distribute it with your commercial product and so on. There's also a getting started free training course on the web if you want to learn quickly. And that's it about about the product, I mean, the high-level description, but I mean, I guess I went fast enough to, for a not-so-quick demo. I'd like to show you OrientDB in practice. Now, how to get OrientDB? That's definitely easy. Open OrientDB.com, click on Downloads. Where's that? Oh, it's the mobile version. Okay. Click on Downloads and get the version you prefer. It's a zip file. Unzip it. Open the bin directory. I'm in the bin directory. And type server.sh if you're in Linux or server.bat if you're on Windows. 3, 2, 1. Up and running. That's it. Now, let's see how it works. When you start OrientDB, you also start a small web server. Inside OrientDB, there is a server that is designed to serve REST services, of course, but it can also expose small web applications like OrientDB Studio. That is the front end for OrientDB. It's a little bit. Is there a chance to have a little less light on the screen? If it's possible, but I mean, it's not critical. Let's log in. I have a demo database here. Admin, guess the password. And here we are. Okay, now let's remove this stuff. I don't want to start with this. Oh, empty stuff. Now, I told you that OrientDB uses SQL as its main query language. Let's see. Let's see the schema. I have some classes. I have class friend and nose that are subclasses of E. E stands for edge. Oops, here it is. I also have person class and topic class that stand V. V stands for vertex. So I have a couple of vertex classes, a couple of edge classes. Let's do a query. Select, star, maybe, let's do this, okay. Is it better? I think so. Select star from person. That's it. And this is my result set. This is plain SQL. I can do select name from person and have only the name. I mean, this is the same SQL you would use in Oracle or SQL Server. This is easy. Okay, let's do something more complex. You see that we have some out, in, friend, nose, and so on. But it's a graph database. I mean, I told you multimodal, document, graph, and so on, and then I'm showing you a table. Why? It's not a relational database. Let's show a graph. Here it is. This is the result set as a graph. Oops, let's see if we can make it more readable. Okay, this is the network of my small network of people. This is my team. There's Luca, Luigi, Frank, and so on. Frank is a friend of Luca. Frank is a friend of Enrico as well, and so on. But I also have other elements I called topic. So, topic. Let's start from topic. Let's add topics. PHP, JavaScript, SQL, and so on. So, Emanuele knows PHP. Frank knows Python. And so on. I'd like to do a couple of queries. So, well, let's see. I don't remember exactly the relationships, but that's okay. Now, okay, that's nice, but let's see how to use it practically. Let's say I want to see who are my friends. How would I do in a relational database? A join, of course. In a graph database, you do something like this. Select from person where name equals Luigi, for example. This is me. Select out, friend. Let's expand the result. Expand the result. Okay. I'm traversing the outgoing edges of type friend. My friends are Enrico, Frank, and Jim. Now I want friends of friends. Out friend, out friend. These are my friends of friends. The performance is extremely good, even if I add new out and again. But you can do more. I mean, this is quite limiting. You have to know how deep you want to go and so on. I can do much better. I can do select from person where name equals Luigi, and then do a deep traversal from there. So traverse out friend from this node, that is me, the starting node, while, I don't know, while depth is less than 5 or less than 500, or while other conditions. I don't know how deep I want to go. While age is greater than 30, I don't know. Just traverse. Just go on. Jump from node to other node to other node, following paths in a graph. You can also do pattern matching. You can do match in version 2.2, just released. Class person as me, where name equals Luigi, Luigi, and then do friend, and get as friend of friend, and then return me.name, friend of a friend.name, my name, and name of my friends of friends. I can do complex patterns. For example, friends of my friends that are also my friends. So I also want that the me is a friend of the friend of friend, as friend of friend. I can define as many patterns as I want. This is describing a subgraph and finding all the matches of that particular subgraph in the big graph I have in the database. All this is optimized, of course. You can use indexes on single nodes. You use deep traversal through links when you have to traverse. You use indexes also when you have super nodes. So nodes that have millions or billions of connections. Now, I'd like to show you something more. You can extend your system. You can extend OrientDB with server-side functions. Let's create a single function. Let's call it hello. This is, I'm in the functions panel. I create the function with a name that is hello. The language is JavaScript. Yes. SQL and JavaScript. How many of you know JavaScript? Okay, you can write functions in OrientDB. Return. Okay, let's add a parameter. Okay, that is name. And I do return hello plus name. That's it. I save my function, and I want to try my function. Luigi, hello Luigi, returns hello Luigi. This is a JSON. The result of functions is interpreted and sent to OrientDB Studio as a JSON object. Now I can use this function in my database as a store procedure. For example, select hello name from person. And it returns hello Luigi, hello Frank, and so on. So I can extend the query language with a function. Inside the function, I have access to the database. So I can do, oh, here it is. I'm sorry for the resolution of the screen. It was supposed to be a little bit bigger, but I mean, I'm in 1024. I can do return db.query, select from person, for example. Let's remove this parameter, save, and let's try it. Okay, it returns a set of records of class person. This one is Luigi. Then there is, who's this? This is Frank, and so on. Now, the nice thing is that you can use functions as REST endpoints. You can do localhost function, the name of the database, that is demo in this case, / hello. Oh, what's going on? Okay, save this password. And it returns a JSON. This is the result set of that query in JSON. I exposed a REST endpoint from the database with a simple JavaScript snippet. Inside functions, you also have control of session and request. So you have the a request object, a response object, something like a session, but that's not actually a full session like what you had in old style servlets, but I mean, something like that. So you can control data type, content type, errors, error message, error codes, HTTP error codes, and so on. Everything inside the database. So, quite powerful. Let's see something more. I only showed you the graph stuff, but let me show you some document stuff. Let's create a person with complex data. Let's do create vertex, but I can do insert, oops, sorry. Insert into, that's the same. Insert into person, set name equals Bob, and address equals a JSON, where street is full street, and city is an RJSON. Say, name London, country UK. Now, this is not text data. Let's run this, okay? I can query the JSON. Let's see if I have, okay. I have bookmark just to go faster. Select from person where address.street like foo and address.city.country.name equals UK. You traverse embedded properties with dot notation. You can do the same for graph traversal. Outfriend.outfriend.name. Outfriend.city.country.name equals UK. All the friends of the friends who are in the UK. I mean, it's extremely easy. There's no join keyword. So you just cannot do join. That's the way to do that. That's easier. Pattern matching, select, traverse. I didn't show you update statements or delete statements, but I mean, you can guess. Update person, set name equals foo, where name equals Luigi. Or insert into person, name, surname, values, foo bar. Plain SQL, delete from person where name equals Luigi. Plain SQL. You already know how to use it. Now, how to start it in distributed mode? Extremely easy. Let's stop the server. Let's do, instead of clear, okay. Instead of doing server.sh, just do dserver.sh. It will, when it starts, it will ask you for a node name. You give that particular node a name. Then you start another one. They just join together, and they start communicating and replicating data. That's it. If you want 3 nodes, just start a new node. This works on your machine, physical machines, virtual machine. We have a Docker image up to date. So version 2.2 that was released 2 days ago, not yesterday, 2 days ago, is already available as a Docker image, official Docker image. There's an AWS image on Amazon. It runs on Elastic, on Azure, Microsoft Azure, and so on. So you can decide how and where to run it. And of course, you can run it embedded inside your Java application. OK. How many seconds do we still have?
Well, you've got a few.
A few. Fantastic. Questions? Oh, no.
You mentioned that they already said
Not working.
basic implementation of sharding. So what about scalability? How does it look currently?
Yeah. The scalability on read operations is guaranteed with multi-master replica. The right scalability can be achieved with asynchronous replication and conflict resolution strategies. We have basic support for sharding. That means that there is no automatic sharding. So you have, I mean, if you want to put this record in that particular shard, you have to, the client has to do that call to that particular node that contains the shard. That's, I mean, managing a sharded graph is much trickier than managing a sharded key value store because you have relationships. traversing a graph, a sharded graph, has a different performance compared to a MapReduce on a simple key value store, on a document store. So you have to design your database in a particular way to avoid jumps from a cluster to another one during the traversal. I mean, you have to be careful to what you do. But, I mean, you can do that. In next release, we will have automatic sharding with sharded indexes and so on, based on sharded keys. So you will have a sharding key on vertices, on edges, and so on, and the clients will automatically redirect, insert, update operations to the right shards, and so on. This will be in version 3.0 that is scheduled for the end of this year.
Thank you.
Complementing.
Thank you.
It is possible to import data from legacy databases into this.
Yeah,
OrientDB?
definitely. With version 2.2, we also released a tool that is called Teleporter. Teleporter is a connector and a translator from relational schemas to document graph multimodal. So you just connect Teleporter to Oracle, to SQL Server, Postgres, and so on. It tries to infer a graph model based on conventions on your relational database. Foreign keys, for example, join tables. It tries to understand if a table is a join table and translates that in an edge. It's also quite smart to understand if you created that relational database using an OR mapper. I don't know, Spring Data, Hibernate, and so on. I mean, Hibernate has its own conventions on column names, on table names, and so on. So if Teleporter finds these particular conventions, tries to understand the object model that was behind that, and tries to use it to create a proper graph inside OrientDB. There's also another utility that is called OrientDB ETL, that is a JSON-based ETL tool that just allows you to describe transformations in simple JSON syntax. So you just define this field has to be translated this way and has to be saved on this class. These things have to be aggregated this way. This table has to become a class like this. This operation becomes an insert here, and it allows you to connect to data sources like JDBC, so relational databases, text files, JSON, so typical data sources you can have.
And do you have any benchmarking? Do you have the performance against another, comparing other databases?
That's a good question. We don't like benchmarks very much. We have some, but every time we take these benchmarks out, someone complains, and someone takes other benchmarks that say the opposite. So what I always suggest is do your own benchmark on your own use case and see how this performance with your data model. Maybe a relational database is much performing for that. Or maybe a graph database like OrientDB is better. I mean, it depends a lot. What I can tell you is that on my Mac, you can do a massive insert without indexes on multiprocessor in the order of tens of thousands or up to hundreds of thousands inserts per second. And you can do deep traversal almost at the same speed. Of course, everything depends on how much memory you have, hot cache, warm cache, cold cache. If you have 50 indexes on the same class, of course, the maintenance, the update of these indexes will take time, so you will slow down insert operations. I mean, there are a lot of trade-offs. This is why I say don't rely too much on public benchmarks from vendors. I can write a benchmark that demonstrates that my product is better than any other product on any use case, but it would not be realistic.
Grazie mille.
And I think that's all we've got time for, unfortunately. But if you want to speak to him right afterwards.
Of course, I'll be around even this evening, so if you want to catch up and ask for questions.
Fantastic. Well, thanks for your time.
Thank you very much.